Alright, welcome back to Why Organic Chemistry Makes Me Question My Own Existence. In this video, we're going to go over chair conformations. Now, since I'm going over the entire chapter of the Bible, also known as the Organic Chemistry textbook, this video is going to be quite long. So let's go over the brief agenda of what we're going to be doing, what we're going to be accomplishing in this video. So first, you should like and subscribe. Next, we're going to go over what are chair conformations. Then I'm going to tell you how to draw one. And then we're going to go over axial and equatorial positions of chair conformations. Then we're going to do ring flips, and we're going to do some painful practice problems, including an extra credit problem here, challenge problem. So let's begin. What is a chair conformation? Well, a chair conformation is basically another way to depict cyclohexanes. Cyclohexanes are basically ring-looking molecules that are made up of 6 carbons, basically like a hexagon. Now, if you're a flat earther, I'm sorry, but you're going to hate me. What we're going to do here is we're going to take a 2D molecule, our cyclohexane, and turn it into a 3D molecule. What? Yeah, that's what we're doing. So this is a chair conformation. It's essentially a 3D molecule of this, a 3D depiction of it. Now let's go over how to draw one. Now what you're trying to aim for is a broken lawn chair. Your figure, your image, your chair conformation should look like a broken lawn chair. That means you hit it on the spot, okay? Now, one thing to take note, this is not an art class, okay? I'm not an art major, you're probably not an art major. If you're an art major watching this video, I don't know what you're doing here. You're free to leave, you're not being, held against your will. Unless you want to learn this, then go ahead. But yes, it's okay if it doesn't look perfect, your professors are usually fine with it. So here's what you do, you're gonna draw a wide V first. So let's do that. Oops. Let's draw it like, no. What am I doing? There you go. Okay, that's good enough. A wide V. Now draw a line going slightly at a 60-degree angle right here. Okay? Then you're going to draw a parallel line from this one, so comparing to this one, a parallel line right here. And then you're going to go here, and then connect the dots like this. And that is your chair conformation, your regular chair conformation. I know it doesn't look the best. I know not all the lines are parallel. What really should be this line and this line are parallel, this, and then this and this. I know they're not parallel, but once again, not an art class. This is chemistry. And it's fine. Okay, let's go over axial and equatorial positions. Now, axial position, so which we're going to do first, think about your axial skeleton. So what I'm talking about here, what axial and equatorial are things connected to the chair conformation, right? For example, if we have, I don't know, like say hydrogen here, oxygen here, I don't know, carbon, this, right? Random crap, okay, around the molecule. Those are the axial and equatorial positions. So it's the stuff connected to the carbons, because the carbons are here, 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 right? 1, 2, 3, 4, 5, 6. So axial. What your axial skeleton is, it's essentially the bones that make up your head, your skull, neck, vertebrae that helps you keep your posture. Basically help you keep, be straight up or straight down. Now, think about this. Wedges will always point up and dashes will always point down. So whenever you see your molecule, your cyclohexane, if you ever see wedges on the chair conformation, they're always going to be pointing up and dashes always pointing down. And don't worry, this will make a lot more sense in a few moments. The equatorial position, think about like the equator. It goes horizontally. However, in the equatorial positions, they are slanted either up or down. So they're going horizontal, but also slanted up and down. And this depends on the axial position to solve. So I know you're probably very lost. So let me break it down this way. Imagine you burn your organic chemistry textbook and you go to prison. This right here, if you memorize this, this is your escape plan for all chair conformations. If you remember this, you can easily do any chair conformation on an exam. This right here is your cheat sheet, your getaway plan. What does this say? Okay, so you'll notice that we have 6 carbons here, right? 1, 2, 3, 4, 5, and 6, okay? Every carbon has one axial position and one equatorial position. Everything in red, all the red lines are axial positions, and anything in the light blue are equatorial positions. So let's look at the axial first. Look at carbon 1. The axial position, carbon 1 goes straight up. On carbon 2, it goes straight down. On carbon 3, it goes straight up. On carbon 4, it goes straight down. On carbon 5, it goes straight up. And carbon 6, it goes straight down. So it's alternating. Every single carbon, every next carbon rotates. Up, down, up, down. Do you remember this in elementary school when you had to do the physical fitness test and you had to do like push-ups or whatever, and they play that recording? Up, down, 1. Up, down, 2. It's giving me PTSD. Anyways, that's what this is. You're just going up and down. So carbon 1 goes up, carbon 2 goes down, carbon 3 goes up, carbon 4 goes down, etc. The equatorial position is the exact same thing. It alternates. However, you'll notice it slants down. So at carbon 1, it goes down, so it's in the down position, but is slanted to the left. In carbon 2, it goes to the up position, slants to the right. Carbon 3 goes down, slants to the right. Okay? So what about the slanting here? So first, let's take care of if it's going up or down. So on carbon 1, it goes down. Carbon 2 goes up. Carbon 3 goes down. Carbon 4 goes up. Carbon 5 goes down. Carbon 6 goes up. So it's alternating. Opposite from the axial. So if axial is going up, equatorial is always going down on that same carbon, and vice versa. If axial is going down, then equatorial is going up. Now, what about the slanting left and slanting right? Here's the cheat code here. Draw an imaginary line straight down the chair conformation. If you're looking at the left-hand side, all equatorial positions will be slanted to the left. You'll notice slanting to the left, slanting to the left, slanting to the left. If you're looking on the right-hand side, all equatorial positions are slanting to the right. Carbon 2, slanting to the right, to the right, to the right. Okay? So that is basically it. This is what you need to memorize, okay? This can apply to basically every single problem for chair conformations. And this will help you, judge where molecules are going to go. So now let's talk about ring flips. Now, by the way, if you're confused on this, don't worry. Practice problems are going to help you. When we do the practice problems, this is going to make so much more sense. I can guarantee you, I can promise it. Let's just explain it to you. Explaining this concept is kind of difficult. Let's talk about ring flips. Now, chair conformations are not stable mentally, okay? They kind of have a little psychotic episode and they kind of flip out. Literally, they flip. So there's another way to draw chair conformations, and that are ring flips. Essentially, this is just an overcomplicated version of saying, when you draw the chair conformation, there's an ability for the chair conformation to switch positions. Basically, what this means is all axial positions, so all the groups you put on axial positions will become equatorial positions, and all equatorial positions will become axial positions. Also, the chair is drawn slightly different, and the carbons are labeled a little differently. Now, I know this doesn't make any sense, but let me break it down for you. First, let's go over how to draw a ring flip. All you do is basically do the same thing, right? Draw the V. Now, instead of drawing like straight down like this, you can draw it like slightly out like this, then like this. That's terrible. Like this, and like this, okay? I know it looks kind of the same, but it's different in a way, okay? So that's your ring flip, how to draw one. Now, here's the important thing. It doesn't really matter how you draw the ring flip, right? Remember, not an art class. Your professors are usually okay with it. What matters is the carbon numbering, okay? So, you know what? Let's actually renumber this one, because I don't like this one, how it's numbered. Let's go back to our cheat code, how I said this. 1, 2, 3, 4, 5, 6. Okay, so this is our normal chair conformation here. The ring flip is going to be numbered slightly differently. All you have to do is move the numbering by one space. So this was carbon 1 here. And then this would be 2, this would be 3, 4, 5, and 6, right? Well, here's what we do. We move the number 1 to this position now. So on the ring flip, on the ring molecule here, we're going to do 1, 2, 3, 4, 5, 6, okay? So all we just did is move the carbon one space over to the next. We move the number to the next carbon. So now it starts, here's 1, 2, 3, 4, 5, 6, okay? Now notice the molecule is still on carbon 3, right? So here's the substituent on carbon 3 here and carbon 3 here. But what's different is this is an axial position, and since when you do the ring flip, axial positions become equatorial positions, this is an equatorial position. And I know this you're probably still lost. So let's do some practice problems here. Okay? So draw both chair conformations, regular and the ring flip, for each molecule. So here we have a chlorine, and we're going to number this 1, 2, 3, 4, 5, 6. So let's draw the chair conformation. So V, this, like this, oops, like this, like this, like this. Good enough. Okay. Here's the chair conformation. Now we number our carbons. 3, 4, 5, 6. Okay. We have a chlorine coming out of carbon number 1 here. Okay. Now, in this specific instance, it does not matter if it's pointing up or pointing down, right? Because it's not a wedge, it's not a dash, we can't really tell. It's just a bond, okay? So this is the simplest case. We're just going to put it in the up position, okay? Just for this example. The other examples will make more sense, but for this one, we're going to put it in the up position. Now you'll notice, let's look at our little cheat sheet here. The up position is taken up by the axial position. So we're going to put this molecule in the axial position. Chlorine. Just like that. And that's the chair conformation. Now let's do the ring flip. Let's draw the ring flip. So it's like this, down, like that. Good enough. Okay. Now let's number our carbons. Now here would be carbon 1, right? And then this would be 2, 3, 4, 5, 6. Well, we move one space over, so now this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. Now, what do? Since this I drew on the axial position, and since ring flips, from axial we must go to equatorial. So we're going to draw this in the equatorial position on carbon number 1. Now, let's look here. We are in this position right here. Even though this is labeled 1, 2, 3, 4, 5, 6, right? We're in this position, right? We're in this position. So the equatorial position is pointing up and to the right. So that's where we're going to draw the chlorine molecule. Like this. Ta-da! Like that. And that is the answer for letter A. Now, I know was very too basic, and basic does not necessarily mean easy. Honestly, these are easier. And this is usually what you'll find on an exam. This is a stupid problem, honestly. You're never really going to get this problem on a test. But this one you probably will. So let's draw this one. We have an ethyl group here and a methyl group here. So let's start numbering. 1, 2, 3, 4, 5, 6. So let's draw the chair conformation. That, like that. Like that, like that, and like that. That's ugly. I'm sorry. Okay, there you go. Now let's number. 1, 2, 3, 4, 5, 6. Okay. The ethyl group is on a wedge. And now I mentioned that wedges are always pointing up, okay, and dashes are pointing down. So this is a really good example here. The ethyl group is on a wedge. So it must be pointing up, like I said. Now let's look at our diagram here. We're looking at carbon 1, right? Because that's where the ethyl group is. Notice the axial position is pointing up and the equatorial position is pointing down. The ethyl group, I mentioned, must be pointing up, right? So wedges will always point up. This automatically eliminates our equatorial position here, okay? Because it's pointing down. Right? It automatically eliminates it. That leaves only the axial position. So this ethyl group must go in the axial position. Okay? The methyl group is on carbon 3 and it's on a dash. Dashes always point down. So let's look at carbon number 3 here. You'll notice the axial position is pointing up and the equatorial position is pointing down and to the right. it cannot be on the axial position because the axial position is pointing up. And I said the dashes must always point down, no matter what. Dashes are always pointing down. So that leaves the equatorial position because that is indeed pointing down. So we are going to draw the methyl group on the equatorial position on carbon 3, pointing down like this. And it's slanted because remember, oops, that's the ruler. We draw an invisible line, and for equatorial positions, right, we're on the right-hand side of the molecule. The right-hand side of the molecule always points to the right. Okay, so let's do the ring flip. So no. Like that. Yeah, it's fine. Good enough. Okay. We number our carbons. And remember, we skip. So this would usually be 1. This would be 2, 3, right? But this is now 1, 2, 3, 4, 5, 6 because this is a ring flip. So 1, 2, 3, 4, 5, 6. Okay. So we do the same thing. So now the ethyl group was on the axial position on carbon number 1. So that must mean it's going to go into the equatorial position on carbon number 1. The equatorial position here looks like this. Like that, okay? The methyl group is on carbon number 3 here. So that's just carbon number 3 right here. It was on the equatorial position, but now we're doing the ring flip, so now it must be on the axial position, which would be right here, right? So we're looking, even though this stays 4, right? Remember, we're doing a ring flip, so we move 1 carbon over. But anyways, we're looking at this position right here. Okay, right? Same position, looks the same, roughly. So all we have to do is draw the methyl group in the axial position because we were on the equatorial position. So you'll notice right here, the axial position goes straight down. So that's where we're going to draw the methyl group. Straight down, like that. And that's the answer for B. So it's not that bad, right? It's pretty simple. Let's do C. C, okay. So let's number our carbon. 1, 2, 3, 4, 5, 6. So let's draw a chair conformation. V, like this, like that, oops, that, like that, and like that. Okay. Let's number our carbons. All right, we have a methyl group on carbon number 1 here. This is a wedge. Wedges always point up. So we're going to look here, carbon number 1 here. Well, notice the axial position is pointing up, so we're going to put it in the axial position because the equatorial position is actually pointing down and to the left. So we're going to do that. Like that, methyl. This is a tert-butyl group here on carbon number 4. It's on a dash. Dashes must be pointing down. So we're going to go over carbon number 4 here. Notice the axial position is pointing down, so it's going to be in the axial position, not the equatorial position, because the equatorial position on carbon number 4 is actually going up. And it must be on it's on a dash, so it must be pointing down. Like that, like that. There you go. That's the answer. That's the chair conformation. Now let's do the ring flip. It's going to go like this, like that, yeah, like that. Okay. Number our carbons. Remember, we hop over 1 carbon here. So 1, 2, 3, 4, 5, 6. Okay, the methyl group was in the axial position, so it must be in the equatorial position for the ring flip. We're looking at this location here. And notice the equatorial position goes up and to the right. So that is where our methyl group is going to go to. Up and to the right. Methyl. Our tert-butyl was on the axial position. So now we're going to go to the equatorial position. We are looking at this area right here. Okay, this like this would match up with this area. So this was the axial position, so it's going to be the equatorial position. The equatorial position is pointing down and to the left. So that is where our tert butyl group is going to point to. Like this, like this, like this, like this. And that's the answer. Okay, let's do the challenge problem. So this is lindane. Now, if you're a fan of insecticides or lice, you would probably know what lindane is. If you don't, then I don't blame you. Lindane, yeah, is to treat lice. Now, this kind of reminds me of those 21-in-1 shampoos you could get at Target, right? One that serves as a shampoo, a conditioner, a lice killer, insecticide, detergent, all the oil for your car, all that kind of stuff, right? So, this is lindane. Basically, it's hell. Chlorine everywhere. So let's draw the chair conformation. It's the same thing, okay? Even though it looks so complicated, it's the same thing. VE, oops. Like that, like that, like that. There we go. Good enough. Let's number it. So we're gonna number this 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Let's do carbon number 1. Carbon number 1 is a dash, so it's pointing down. Since this carbon number 1 here, we look at our little cheat sheet here, the axial position is pointing up. And we need it to be pointing down. So we're going to take the equatorial position because the equatorial position is indeed pointing down. So it's going to look like this. That. Okay. So let's do carbon number 2. Carbon number 2 is on a wedge. So since carbon number 2 is on a wedge, it must be pointing up. Okay. So, so here we are. Since the equatorial position is the one pointing up, not the axial is pointing down, right? It's going to be on the equatorial position. Right, pointing this way. Carbon number 3 is on a wedge, so it must be pointing up. On our little cheat sheet here, the axial position is the one pointing up. So that's the one we're going to use, because that's what we need. So, pointing up, that. Carbon number 4. Carbon number 4, we're on a dash, so it must be pointing down. On carbon number 4, it is indeed the axial position that's pointing down. So, that's what we're going to do. Carbon number 5 is a wedge. Wedges always point up. So, on carbon number 5 here, on a little cheat sheet, the axial position is the one pointing up in this circumstance. So, we're going to use the axial position here. And carbon number 6, we have a wedge. Wedges point up, so we look at carbon number 6 here. Axial is pointing down, which is not good, so we're going to use the equatorial position, which is pointing up. And then it's pointing up in this direction here. Like that. There we go. That's the answer. That's the chair conformation. Now let's do the ring flip. The ring flip, let's draw it. V, this way, this way. Yeah, that's fine. Once again, not an art major. I can't even draw a stick figure, right? So look at this. It's fine. That's actually one of the better ones I've drawn. Okay, so we need to move one carbon over now. So this is going to be 1 now. This is 2, this is 3, this is 4, this is 5, this is 6. Okay, on carbon number 1, the chlorine was on the equatorial position, so it must be on the axial position now on carbon number 1. So we look at here, we're looking at this one, right? Because this kind of matches up with this. It looks the same. So, like the position looks the same. And the axial position goes down. So that's where the chlorine is going to be. It's going to look down. Like that. Okay? Carbon number 2, we are on the equatorial position here. So it must be on the axial position. So we're going to look over here. Axial is going straight up. Sweet. Carbon number 3 is on the axial position, so it's going to be on the equatorial position. Okay? So for the equatorial position, it is pointing this way. So, chlorine here. Carbon number 4, we have it pointing on the axial position. And then, so we look for here, we're corresponding there. And then, so we're looking at the equatorial position, so we need the equatorial position. And it's going to be pointing this way. Okay, carbon number 5 is an axial position. So we look here now, and this is to be in the equatorial position because we're dealing with this one, so we're going to deal with this one. And like this. And carbon number 6. Carbon number 6 is in the equatorial position. So we need to be on the axial position, and axial position here, because it matches up here, it aligns like that. It's going to be pointing up. And that's the ring flip. That's the answer. So, if you found this video helpful, please like and subscribe. If you want more problems like this, I can definitely do more problems, so just let me know. Until next time, later.